You've probably heard of inverse functions before, or the idea of an inverse in math, which is often informally just thought of as being the opposite. We say the inverse of something is, in our heads, the opposite of that. And let's come up with a little bit more of a formal definition of what an inverse function might be using our understanding of composition functions. We can define an inverse function as such. We would say if f composed of g of x results in x, and g composed of f of x also results in x, then we would say that f of x and g of x are inverses of each other. And let's think about why that is the case. Because if one function composed of another function results in just x, what we're really doing is we are undoing the operations of the other function. So if, for example, if you said that g of x, let me actually make this a little bit smaller. If we said that g of x were equal to, let's say, x plus 2, and f of x were equal to x minus 2, if we were to do f composed of g of x right now, f composed of g of x, we would effectively be plugging in x plus 2 in for our input here. So we would say x plus 2 minus 2. Well, what has that f of x done? It has undone the operation of g of x because x plus 2 minus 2 results in just x. So we would say that f composed of g of x is just x because f of x has undone the operation of g of x. And if we did g composed of f of x, well, this time we're doing some input plus 2. And what is that input in this case? Our input is x minus 2. And also, we get x. So two functions, if their compositions both result in x, then we can say that those functions undo one another and therefore can be written as inverses. And notation-wise, we would write this as the following. We would say f composed of g of x can also be written in the following. F composed of the inverse. This kind of f to the negative 1 power, this is not referring to a reciprocal, but the idea of an inverse. So we would read that as f inverse of x. So f composed of its inverse should be equal to x. Now, important question. What relationship must exist between the domain and ranges of the two functions? And the short answer is that the range of g of x, or the inverse, is the domain of f of x, and vice versa, or versa vice, depending on how you want to think about it. That is to say, the domain of f becomes the range of the inverse, the range of the inverse. And the range of f becomes the domain, or is the domain, of the inverse. Okay? All right, so now that we've thought about that for a second, let's try some practice problems where we want to verify that functions are indeed inverses of each other. Let's use composition to do that. So, first off, let's verify that f of x and g of x are inverses using composition. So first off, let's find f composed of g of x. F composed of g of x. Well, f of x says you're going to take your input, square it, and you're going to add 1. And g of x here is root x minus 1. So this is going to give us x minus 1, which is the result of when we square a radical, plus 1. And that's equal to just x. Now let's try g composed of f of x. G composed of f of x. Well, that's the square root of our input minus 1. Well, what's our input? X squared plus 1. Well, square root of x squared plus 1 minus 1 is just the square root of x squared. And we can just say that that would behave as x. Okay? Or the absolute value of x, because we're just looking at the principal root. Now let's take a moment and let's take a look at the graphs of these two functions here. Okay? What do we notice about these functions here? So first off, I just want to double back to this. Make sure that we've just confirmed f composed of g of x is x. G composed of f of x is x. Therefore, we can say that f and g are indeed inverses of each other, are inverses. Well, now that we've confirmed that these two functions are inverses of each other, let's look at their graphs. So I'm going to just go ahead ahead and just plot something pretty basic here, nothing too fancy. Just want to sketch a basic idea here. Well, what does f look like? Well, we're told f is x squared plus 1. So x squared plus 1. So I'm going to graph f in the same color that, let's see, let's just say f is blue. So x squared plus 1. So y-intercept of 1. And then we have the parabola, something like this. And I provided what's called a domain restriction here so that I don't have to worry about anything else. And we'll go over why exactly I wanted to provide that in just a moment. But that function is x squared plus 1 when x is greater than or equal to 1. So this function is going to look something like this. Now, let's try in red now, g of x. What does g of x look like? Well, it's a radical function with a horizontal shift of 1. So this graph looks something like this. And what do you know about these? What do you notice about these two functions here? And if you really need to, you could actually also look at the table of values. So let's just quickly do that. For f of x, we saw that when we had an input of 0, we resulted in 1. 1 gave us 2, and 2 gave us 5. Compare that to the input and output of g of x. Here, 1 gave us 0, 2 gave us 1, and 5 gave us 2. Hopefully it's become really clear now. The domain of one function is the range of its output. I'll say that again. The domain of one function is the range of its inverse. And the range of one function becomes the domain of its inverse. Graphically, what does that look like? It would see that these two graphs are symmetric over the line y equals x. So we can see here very efficiently when we're finding inverses graphically, we can just simply switch our x and y values. And let me just write the kind of big takeaway from the graph here. The graph of f and its inverse, f inverse of x, are symmetric over the line. So we see here that with inverse functions, one, if we can show that the compositions of the two functions are indeed equal to x, we can verify that they are indeed inverses of one another. Graphically, we see that inverse functions are symmetric to one another over the line y equals x, and we can very quickly graph inverse functions by simply switching their domain and range, because the domain of one function is the range of its inverse. So with that being said, go ahead and try to verify these next two practice problems on your own. So continuing on in our lesson, so we just briefly talked about this. And so really to hammer it home, understanding that if a function has an inverse, we can switch the x and y to graph the inverse, okay? Because it must be symmetric over the line, y equals x. So very simply, if this point down here, for example, for this function is -1, -2, what point must exist on its inverse? Well, you must have, let me do this in a different color. Let's go orange. -2, -1. That inverse must exist. What about this point down here? 0, -1 should result in -1, 0. We'll try to pause the video and finish up the rest of this graph. 1, -1 should give us -1, 1. 2, 0 should also have 0, 2 if we're finding its inverse. And 3, 1 should give us 1, 3. So we can just very cleanly start graphing its inverse as such. Okay? And again, you can see that it's symmetric over the line y equals x. That's not a great y equals x line, but you get the idea. Y equals x. Okay? Now look at what we just graphed carefully and ask yourself, is this inverse that I've just graphed, is it a function? And the answer is no. This inverse is not a function, because if I were to draw a vertical line through this portion of the graph here, I would see that for the input -1, I've got two outputs. Therefore, this inverse, although it's a graphical inverse of our original function is not actually a function by definition. It does not satisfy the definition of a function. We've got an input giving multiple outputs. So when does an inverse function exist? We say that a function f of x has an inverse if and only if, that's what this little notation here means, if and only if this function is one-to-one. Well, what does one-to-one mean? It means that every input has exactly one output. That's the definition of a function. It satisfies that. But also, every output, every y value, corresponds with exactly at one input. Okay? So to say again, a function is one-to-one if every input has just one output, which makes it a function, but also every output has exactly one input. And how can we see this graphically? Well, going back to this, we can say to our original function, if it crosses what's called the horizontal line test. That is, I can draw a horizontal line and it should not cross more than once through the graph. So look back at our original function here. If I were to draw a horizontal line at x or y equals -1, notice that right here, it is crossing through more than one place, which tells me that the output of -1 has multiple inputs corresponding with it, which tells me that when I reflect this over the line y equals x, that graph, that reflection is not going to cross or pass the vertical line test. Right? And that's really logical. If an output has more than one input corresponding to it, then for its inverse function or its inverse, it's not going to be a function because every input then will have more than one output. So it's a way of determining whether or not a function will have an inverse before you go through the trouble of graphing it. So if it crosses the horizontal line test, it tells us that every output has exactly one input. So to finish this up, what that means often is that if a function is not one-to-one, what we can often do is restrict the domain of that function so that it is one-to-one. So the best example of this is looking at a quadratic. Look at x squared. First off, is x squared a function? And the answer is yes. It passes the vertical line test. Every input has exactly one output here. Now, is this function one-to-one? And the answer is no. In almost every spot except for when x is equal to 0. If I draw a horizontal line, it crosses more than once, which tells me I've got an output, for example, of 1 that corresponds to multiple inputs. In fact, an infinite number of inputs. Therefore, or I should say not infinite, excuse me, just two inputs here. So the quadratic x squared is not one-to-one. So the question then is, how can I restrict the domain so that this function would be one-to-one? Pause and think about that. Well, there's multiple ways to restrict the domain, but probably the easiest one, maybe in this case, would be to restrict the domain so that we're only looking at this part of the graph. That is to say, we restrict the domain so that we're looking just from all values that are less than 0, less than or equal to 0, in fact. Now, if I reflect that over the line y equals x, that would look like this, what we have here. Now, is this graphical reflection here, or this inverse, is it indeed a function? And the answer is yes. Its inverse is a function because it passes the vertical line test. So what we've just successfully done is we have restricted the domain of this quadratic such that its inverse is indeed a function. And if I wanted to, I could have also restricted the function here. For example, actually, let's do that in the highlighter. Let's just say I could have restricted that, so I'm looking just at x is greater than or equal to 0. And that's fine. We could have done that as well. All that means is that its inverse is going to now look like this. And I can continue this on, such that way. Okay? Oh, and now that I actually look at it, now that I think about it here, I think I actually messed up my inverses and kind of which corresponds with which. Sorry, what I had highlighted in green here. If you think about these points, this would be, for example, 1, 1, and up here, this would be 2, 4. That actually should have corresponded to what I initially had up here. So this actually is, this, I apologize, is the inverse of what I have highlighted in green. And if I wanted to graph the inverse of what I had in red, let's just switch color so I can match this up. So I wanted to find the inverse of what I had in red. This would be -1, +1, -2, +4. So on this graph here, we should have 1, -1, and then 4, -2. So 4, -2 down here. That's what this inverse would look like. Something like that. Okay, so apologies for the confusion. All right. So with that said, let's just quickly go through these functions here. And I'll let you determine which of these functions here are one-to-one. But let's try a problem like, for example, something like 1. Actually, let's just go through them. We just said that this function was not one-to-one. What about x cubed? This function is one-to-one. What about the absolute value of x? Well, that graph looks like this. This function is not one-to-one. And what about something like this? This is just a parabola with a bunch of transformations, so this also would not be one-to-one. Okay? All right, well, hopefully this helps break down what an inverse function is, how we can define an inverse function, and also how we can restrict the domain of certain functions such that it would be one-to-one.